Let me move now to GPU computing. We've always felt that heterogeneous computing, parallel computing, could really revolutionize computing because of its characteristics. You could use the CPU for single-threaded performance where single-threaded code is. You could use a parallel processor for massively parallel complicated problems. And so there's all kinds of applications for such a thing. It would be higher performance, the speed up would be phenomenal, and it would be the most efficient way, the most energy efficient way of doing computation. The challenge for us was, how do we take a brand new computing model? You know, we're familiar with using C compilers and high-level programming constructs, and we run it on basically the microprocessor architecture of today. How do we take this brand new architecture and bring it to the world? It's a bit of a chicken or egg problem. On the one hand, if there are no applications that are heterogeneous, why would somebody buy a computer with a parallel processor inside? And if there are no computers with parallel processors inside, how do you create the install base to inspire software programmers to go create software for such an architecture? And so that's the classic chicken or the egg problem. 10 years ago, we came to a realization that maybe the GPU is the perfect platform, the perfect vehicle to bring this new architecture to the marketplace. And the reason for that is several folds. Number one, computer graphics is inherently programmable. It's inherently parallel. If we could extend the architecture so that it could be more general purpose, not only would we be able to expand its ability to program and run applications from all different fields, we could also push computer graphics to the next level, from programmable shading to now computational graphics. The two examples that I showed you this morning would not have been possible without CUDA. The second thing, of course, is that the GPU had a day job. It didn't need any applications to go to market. It already has a day job. The day job is called computer graphics. And so with that inspiration, we decided to take CUDA to market, make every single one of our GPUs CUDA compatible, and look what happened. GTC happened. The impact to the industry is really hard to even express. And every year I give you guys a status report. In 2008, we had 100 million GPUs that are CUDA compatible, 150,000 CUDA downloads. 150,000 is a lot of different programmers downloading it, and we had one supercomputer that was powered by Tesla. 60 universities were teaching parallel programming courses using the GPU, using CUDA, and there were 4,000 academic papers. This year, nearly 500 million processors, CUDA processor, have been shipped. You couldn't go anywhere around the world without getting hit by one. If you wanted to program parallel, if you wanted to program using CUDA, you just had to run down to the local store. 1.6 million times it's been downloaded, the CUDA programming kit, and now 50 supercomputers around the world. 640 universities. That's a lot of universities. I really appreciate all of you evangelizing and teaching the next generation how to think in parallel, how to program in parallel. And of course, the work that you guys do in research, 37,000 papers. The industry support has been phenomenal. This is what it looked like at the important supercomputing conference in 2008. All the greens are partners of ours or OEMs or vendors who are somehow promoting parallel computing, somehow promoting Tesla. This is what it looks like this year. That's about 50, by the way. This is what 2012 supercomputing looks like, and it is almost completely penetrated. It's very clear that we are close to the tipping point. If we're not at the tipping point, we're racing at it. If we're not at a tipping point, we're racing at it. And in fact, you could kind of see from the top 500 supercomputers. These are early adopters of technologies, but these are informed adopters. They're building these computers for scientific applications, for scientific research. They're building these computers for real work. They're building these computers so that they can inspire science that could save lives. This represents about 20% of the overall, of the total top 500 computing horsepower. This year, we represented 20%. And so it's going to be really interesting to see what happens next year. Out of that includes the world's most powerful, the world's most advanced supercomputer, the Oak Ridge Titan. The Oak Ridge Titan has been in operation now for some time, and I'm pleased to say that not only is it the highest theoretical performance supercomputer, it also just recently did the world's largest solids mechanical simulation. At sustained of 10 petaflops, 40 million processors, 40 million CUDA processors. I can't even fathom that. 40 million CUDA processors came together to solve a singular problem and deliver 10 petaflops of sustained performance, which is 5 times larger, 5 times faster, 5 times, however you think, more complex than anything achieved up to that time. This week, the Swiss Supercomputing Center announced that they are also going to adopt the Tesla GPU and build Europe's fastest GPU supercomputer. They're going to be using it for weather simulation so that they can predict weather very accurately a day to up to a week in advance, getting people out of harm's way. A whole bunch of other research is going to be done on this supercomputer called Pizdant. Pizdant, I think, is the tallest mountain in Switzerland. So now we have major supercomputing centers and large supercomputing installations in Japan, in China, in the United States, in Europe, and many others. Really, really exciting to see that we are racing at the tipping point, if not at the tipping point. But nothing is more exciting, really, than, frankly, the research that is being done. You guys are all here to showcase your work, to learn from other people's work. There's just some amazing science being done here. I didn't know that the human genome wasn't just a double helix. Apparently, that's only the short strands. Tomorrow's keynote is going to be really interesting. Apparently, that our genetic code could be up to 2 meters long. And somehow this 2-meter code is somehow compressed and condensed in a 3-dimensional way into a nucleus of a cell a few microns wide. And somehow it doesn't knot up. And somehow, depending on the way that it's folded, the same genetic code will store different information so that it could be a liver cell or it could be a something else cell. Amazing insight. The scientists at Baylor and Rice are going to talk to you about how they discovered this and how they used the GPU to decode their discovery.